Thank you for introduction. So in this talk, I will talk about the tensor scaling, the entropic tensor scaling algorithm, and some purely mathematical results. Okay, so let's talk about tensors. So actually, our results generalize to any B tensors, but for simplicity in this talk, I will stick to only 3 tensors. So I will denote T for a complex tensor. And as you know, 3 tensor can be considered as a 3D array of complex numbers. Then you can naturally consider the apply matrices to your tensor and define it in this natural way. Then we say your tensor T restricts to S when S is obtained from a tensor T by matrix application. And then we can consider its asymptotic version, asymptotic restriction, which is defined by this equation, where the square cross means the Kronecker product. I will explain later. But intuitively, it means that so you have a quantum state S, and then the S to the M means the M copies of S. That means that the M copies of S is obtained from some M plus some more copies of T. And this holds for all M. But the small OM notation means that this has to be increased slower than the linear function of the M. Okay, and why is this important? So first, this asymptotic restriction captures the asymptotic subrank and subrank of tensors. So it's particularly important for the connection to the matrix nullification exponent. And in the quantum information, such a restriction is considered in the resource theory. And for example, one example is that the well-known W tensor cannot asymptotically restrict to the GHZ tensor. So it's not straightforward from the definition, but in this talk later, I will explain why. Okay, and for this asymptotic restriction problem, Strassen constructed the theory of asymptotic spectrum, which is as follows. So let's X with a set of a function phi defined on all 3 tensors that satisfy the following. So first, phi evaluated at the very simple 1 by 1 by 1 unique tensor has to be 1. And second, phi has to be additive on the direct sum of tensors. And third, phi has to be multiplicative under the Kronecker power of tensors, and where the Kronecker power is defined as in the picture. And lastly, phi has to be monotone, which means if T restricts to S, then phi S has to be smaller than phi T. And such a function phi is called a spectral point. And a crucial point of the Strassen theory is that these functions completely characterize the asymptotic restriction. It means so if T asymptotically restricts to S, then if only if for every spectral point, phi S has to be smaller than phi T. And up to now, the only known spectral points are so-called quantum functions, which I will explain in the next pages. Okay, so for this one, first we consider the flattening of tensor. So it's just like this. So tensor is like a 3D array. Then you can consider its slices, and you split into slices, and you just put the slices next to each other. Then you obtain this bit n1 times n2 n3 matrix, which is called flattening. Then using this flattening, it's a flattening dagger flattening normalized by this norm is which we call this new one is one body marginal of tensor. So by definition, it's a PSD matrix of n1 times n1 shape and has trace 1. And in a similar way, we can consider two different one-body marginals by using the different direction of flattenings. Okay, and such a concept is very natural in quantum information. So the tree tensor can be considered as a pure state on three particles. Then in this case, the physically mu1, mu2, mu3 mean single particle marginals on each local particles. And actually, the one-body marginal, the term borrowed from the quantum information. Then we can define entanglement polytope using the one-body marginal. So for tensor S, there are three different one-body marginals. Then you consider the spectrums of each marginals, and you consider the tuple. Now you consider such a tuple over the all GL orbit of your tensor T. Then finally, you take its closure, its Euclidean closure, then it's called entanglement polytope. And the term shows that this set is actually a polytope in the Euclidean space. And the one important property is that this entanglement polytope is invariant under GL action. And it has an essential connection with what's called the quantum marginal problem, which means for a given vector x, this formula has to determine if x is in the entanglement polytope of a generic tensor. And this polytope has a generalization to other representations. So in this context, this polytope is also called a moment polytope. Okay, now we are ready to define a quantum functional. So we first fix that parameter theta, which is in the probability simplex. So which means theta 1, theta 2, theta 3 are the non-negative values, and they sum up to 1. Then we define a quantity which we denote E theta. This is the maximal value over the entanglement polytope of your tensor of your convex combination of channel entropies. And since the entanglement polytope is the set of spectrums obtained by the GL action, this value is also denoted as written as this. So sup over the GL orbit of the corresponding function. Okay, and the exponential of E theta is known as a quantum function. And Persano, Farna, and Sutton showed that the quantum for any parameter theta, a quantum functional is a spectral point. And one property of the quantum functional is that if the parameter is strictly positive, which means all of the theta 1, theta 2, theta 3 are positive, then a quantum functional takes its maximal positive value if and only if the uniform marginal is in the entanglement polytope. So it means your tensor is semi-stable. Okay, then the central question in this talk is the computation of quantum function. So we want to compute this quantity, but to the best of our knowledge, no efficient algorithm has been known up to today. So you might think that so your quantum function is defined as a concave maximization over a polytope. So you might think that it's an easy problem. But actually, the difficulty lies in the complexity of the entanglement polytope. So actually, the entanglement polytope is a very, very complex object. So actually, recent method for computing the entanglement polytope is only fractal up to 4x4x4 tensors. So for larger tensors, we don't know how to compute the entanglement polytopes. So what we did is that instead of computing the entanglement polytope, we directly compute this maximal value by a simple scaling algorithm, which we call the Entropic tensor scaling algorithm. So which is denoted as follows. So you have your current tensor, which we call TK. Then you compute their one-body marginals, and then you apply their negative real power to your original tensor TK. Then you obtain the next tensor TK plus 1. Okay. And we showed that this algorithm computes the quantum functionals at the rate of inverse of the iteration count. And so the K tensor approximates the quantum functionals with the error of K inverse of K. And moreover, the constant in the big O notation is polynomial of the input size. If your tensor is a integral tensor, so if each element of the tensor is integer, then it's a polynomial time. So I would say that this is the first efficient algorithm for computing quantum functional. And also, when theta is strictly positive, if theta 1, theta 2, theta 3 are all positive, then actually each marginal converges to the identity matrix. But if it's possible, if the corresponding uniform point is in the moment polytope. So this entropic tensor scaling algorithm also works as a new algorithm for the tensor scaling problem or computing the normal form of the tensor. Okay, let's take some examples. For this one, we fix theta as one third. Then in this case, the entropic tensor scaling algorithm is just computing 1/6 power. Then let's compute the quantum function of the W tensor. So in this case, each marginal is 2/3, 1/3. So if you apply this iteration one time, then you can calculate T1 as this one. But the crucial point is that this is proportional to the W tensor. So in this sense, the W tensor is a fixed point of this algorithm up to constant multiple, up to scalar. So this means that the W tensor itself gives the value of the quantum functional, and this is the binary entropy between 2/3 and 1/3. Okay, then let's take the G-state tensor, so which is the 2x2x2 unit tensor. But for in this case, we can conclude that the quantum functional value is the binary entropy between half and half. This is because entropy is maximized once the uniform marginal is in the entanglement polytope. So as a conclusion, for this parameter, the quantum functional of the G tensor is strictly larger than the W tensor. So this obstructs the asymptotic restriction. So this shows that the W tensor cannot asymptotically restrict to the G tensor. Okay, and actually our framework generates to more general convex optimization. So this is written as follows: so minimization over the entanglement polytope, and now you of this function has to satisfy low synchronous convex and symmetric in each argument, which means if you swap two elements inside the same part, then it has to be the same value. And under this condition, of this function can be generalized to Hermitian matrices by taking a spectrum. And the quantum functional case corresponds to the case where S is the negative entropy. Okay, and for this generalized version, we propose this descent algorithm. So this is you have your tensor Tk, then you multiply the matrix exponential of negative gradient of your vector function. Then you obtain the next tensor. So in the quantum functional case, which corresponds to the this function, the negative entropy. So the crucial point is that the exponential matrix exponential of negative gradient of entropy is the negative power of your marginal. So in this way, we obtain the entropic tensor scaling formula. And what we showed for the convergence theorem is that if this function is smooth, which means the Hessian is upper bounded by some constant, then by taking the step size to be the essentially inverse of the smoothness parameter, your kth value converges to your optimal value at the rate of the inverse of the iteration count times the polynomial of input size. So actually, this general version has an application in the G-set rank. So for a positive parameter, Dirksen introduced a new rank notion for tensors, which is called G-set rank. And one property for G-set rank is that its inverse is written as the minimization problem over the moment polytope. So this corresponds to the case where your objective function is some scale infinity norm. And here's one problem, that this objective function is not smooth. Actually, the infinity norm is not differentiable. So in order to prevent this problem, we can use the smooth application of the infinity norm. Then by using the smooth application and applying the general result, we can conclude that the inverse of the G-set rank can be computed up to any predetermined error. Okay, so now we now show that the perspective of this minimization problem gives not only the algorithmic result, but only the very purely mathematical result, which is we call minimax formula. So in order to present this result, we first define the support polytope. Okay, so for a given tensor, consider the perfect distribution on the element of the tensor. But here's a constraint. So in order to put positive weight on some element, then the corresponding tensor has to have non-zero elements on this place. Then you consider the marginal of the probability distribution, and then you consider all the set of the marginal probability distribution obtained in this way. So this is called the support polytope, and we denote omega t. And the crucial point is that this polytope is purely determined by the zero and non-zero arrangement of the tensor. So, and what we show is that for the present minimization problem, we show that the minimized value is the same, is represented as the max over the GL orbit of the tensor of the minimum value of the minimization problem over this support polytope. So this means that this value is completely characterized by the zero and non-zero patterns obtained by the GL action. because the right-hand side is characterized by the zero and non-zero patterns. Okay, and in the quantum functional case, it's very known that the left-hand side is the definition of the quantum functional, some negative log of the quantum functional. And the right-hand side expression has been known as the minus log of the what's called support functional, which is introduced by Strassen. Now we have that by the minimax formula, these two functionals are the same. So maybe I should talk about the history a bit. So first, Strassen constructed the support functional as a candidate for the spectral point. And so actually he conjectured that this is a spectral point, but he only proved that the property for a small subset of the tensors. And for the relation to the quantum functionals, only this direction of the inequality has been known. And again, for a small subset of tensors, that inequality has been known. But today, we solved his very old conjecture, which is more than 35 years old, by showing that these quantities are the same. So actually, we know that the support functional is actually a spectral point, but it doesn't give a new spectral point. Okay, so this is my summary. So our target problem is the minimization problem over entanglement polytope. And it captures the quantum functional when S to be a negative entropy, and GC rank when S is a infinity norm. And we show that it's computable by a simple descent algorithm. And it also is completely characterized by the non-zero patterns obtained by the GO action. And the math behind here is, which I didn't explain today, is just for the convex optimization over Hadamard manifold. And actually, Hirari's recent generalized gradient flow plays a particularly important role here. Okay, thank you for attention.
People think you can explain a little bit of the.
Okay, so actually, Michael talked a bit about this relations. So you consider this polytope as a gradient set of a convex function. But this convex function is on a curve manifold, and so in this, and the particular important keyword is the mirror descent. So which is originally defined in the Euclidean space, but we can generalize mirror descent to this setting. Then we obtain our algorithm as a generalized mirror descent. Thank you.
Person.